Okay, now I've rewritten the problem in terms of the demand equation, right here, plucked out the relevant information. I know, again, Q is a function of time and P is a function of time. So quantity demanded and price. I don't explicitly know what they are in terms of T, but I know they're functions of T. They depend on time. Okay, they're changing in time because they're rates. And what the question was really asking is, what is dq dt when I know that P is $49.75, so each chip is priced at $49.75 a piece, and when demand is 11,000 units per month. Okay, so when P is $49.75 and Q is 11 units, 11,000 units. Okay, but this is in thousands. We'll change that at the end. And when that price is changing it's decreasing at a rate of $1.50 per week. So again, it's the dp dt is a negative 1.50, right? So a negative $1.50. Okay, so that's all I'm looking for. So once I strip away all of the wordage here and turn it right into mathematics, this is all it is. I need to figure out, I have this demand equation, and I need to calculate the relation between the rate at which demand is changing with respect to time and the rate at which price is changing with respect to time. If I get those relations properly, then I can actually answer this question. Okay? So to do that, what I'm going to do is I'm going to take the derivative of this whole equation with respect to time. Okay? Because I want to know how things are changing with respect to time, everything. So when I do that, I take the derivative with respect to t of this whole equation up here. And when I do that again, I have to take the derivative with respect to t of each individual piece of this equation, right? Every single term. Okay? So what I'm going to do is, you can certainly multiply this out first, or you can actually think of this as a product rule, right? This is a product of two things, and this is just a constant, so the derivative of this with respect to time is going to be 0. Okay? So when I do this, I have to take the product. The derivative of a product. So the derivative of the first chunk is just q squared plus 80 times the second. So this is going to be p times d dt of q squared plus 80 plus the other way around, q squared plus 80 times the derivative of p with respect to t. So this is going to be q squared plus 80 times dp. dt should equal 0. Okay? So I use the product rule on this product of things. Here's one chunk, here's another chunk, and the 10,000, which is going to be 0. That's not changing with respect to time. Okay? And now what I can do is just take the derivative of this part and expand a little bit. So when I do that, I'm going to get p times 2q dq dt, okay, plus 0 plus, this is going to be q squared plus 80, all multiplied by dp dt is 0. Okay? So what I did here is, again, I have this, really this is a chain rule going on here, right? I didn't explicitly write it down, but again, what's going on is the q is the inside bit, the outside is I'm going to square it. So what I do is I have to take the derivative of the outside, where q is my unknown. The 2 comes down, I leave the q alone. And then I take the derivative of the inside, because I know q depends on time, right? There's no t here, but in order to get to t, I have to go through the outside part, and then I have to go inside, knowing that q is a function of time. Okay? So I skipped a step here, but really what's going on here is it's a composition of functions. All right? So when I do that, I now have this expression, okay? 2q dq dt. The derivative of t with respect to 80 is 0. And this chunk stays alone because this is just multiplying this dp dt. Okay? So now I need to rewrite this so I can get relations by themselves. In particular, I'm looking for this unknown, dq dt. So I need to solve for dq dt. Okay? So doing that, I'm going to take all this stuff on one side of the equation and isolate the dq dt on one piece of the equation. Okay? So when I do that, I now have 2pq over here. This is dq dt. Is equal to, this is a minus quantity, q squared plus 80, okay, dp dt. Okay, I just took this and I subtracted it by both sides. Okay, and now what I'm going to do is divide both sides by 2pq, and I'm going to have dq dt by itself, which is what I was looking to solve for in the first place. Okay, so when I do that, I actually get that, again, dq dt is going to be equal to all of this stuff over 2pq. Okay, so I just erased a little bit to simplify, but you should check. I just divided both sides by 2pq to get this. So now I know that dq dt is equal to a minus quantity q squared plus 80 over 2pq, all multiplied by dp dt. Okay? So I know these are how the relations relate to one another. Here's my relation, right? Or here's how they rate, or the relation, right? Here are the rates, and here's my relation. Okay? So now all I need to do is to put in these values to find out what this is at this particular instant. Okay? And so I'm going to do that. Okay, so I've rewritten, cleared this up a bit. dq dt is related to dp dt by this relation. Again, I need to plug these values in to calculate what I was looking for, my unknown, which is how is demand changing with respect to time at this particular instant, knowing that price is decreasing at $1.50 per week, and when each chip is priced at $49.75, and the company expects to sell 11 units. There's a demand of 11,000 units. Okay? So let me write this out. So what happens here is I just put in my values. I get a minus. Q is equal to 11. So this is 11 squared plus 80 over 2 times 11 multiplied by P, which is going to be $49.75. dp dt, which is minus 1.50, right? So minus $1.50. And again, when I expand this a little further, I get 11 squared is 121. Okay, so this is a minus 121 plus 80 over 2 times 11 times 49.75 times a minus 1.50. Okay, so I multiply this out to find out what dq dt is. So after I've computed the actual value, I get that it's exactly 301.5 over 1094.5. Again, you should check this with these numbers. And that gives me an approximation of about 0.275. That's how the demand is changing with respect to time. Okay? And remember that Q was in thousands of units. So what I'm going to do is I'm going to rewrite this in terms of the actual thousands of units. And again, what I'm going to do is multiply this by 1,000. So when I multiply this by 1,000, actually this is going to become that the demand, that is dq dt, is changing at about 275 chips per month. Okay? So that means that after I've done all of this, even though I don't know what Q is in terms of T, and I don't know what P is in terms of T directly or explicitly, I can still use related rates, implicit differentiation, to figure out how they relate to one another, how one is changing with respect to the other quantity. So that is, if I know that price is decreasing at a particular rate, then when these chips are priced at some particular value and when the demand is at some particular demand level, I can tell you, at least give you a rough estimate of how the demand is changing at that one instant in time. Okay? And I know the demand is definitely increasing at a rate of about 275 computer chips per month. And again, this makes sense because since price was decreasing, I know that demand must increase. Okay? So I know it's positive, and in fact, this is the actual value I get. The demand is increasing, again, at a rate of 275 chips per month when the demand level is at 11,000 units and the price is priced at $49.75 per chip. And I also know that the price is falling at a rate of $1.50 per week.